Look around you for a moment. A book rests on a table. A car moves at a steady speed. A passenger lurches forward when the driver suddenly presses the brakes and the seat belts restrain the passenger. What connects all these situations? The answer is force. And just as importantly, what happens when the forces on an object balance. In this video, we begin our study of Newtonian mechanics. We will examine what forces are, how forces are classified, why force must be treated as a vector, and how mass is connected to inertia. We will then use these ideas to understand Newton's first law of motion. A common misconception is that a moving object must have a force continuously pushing it forward. Newton's first law tells us something very different. An object does not need a net force to keep moving at constant velocity. A net force is required only to change its velocity. By the end of this lesson, you should be able to look at force diagrams, determine the net force, and predict whether an object's state of motion will change. Before starting Newton's first law, let us briefly meet the scientist whose work organized these ideas into a powerful theory of motion. Sir Isaac Newton lived from 1642 to 1727 and made foundational contribution to physics and mathematics. Newton formulated the basic laws of mechanics that connect force and motion. These laws allow us to explain the motion of objects ranging from a ball rolling across the floor to planets orbiting the sun. He also developed the law of universal gravitation, which describes the attractive force between masses. The same gravitational interaction that causes an object to fall toward Earth also helps govern the motion of the moon and the planets. Newton independently developed a form of calculus, a mathematical tool that became essential for describing quantities that change continuously, such as velocity and acceleration. He also conducted important work in optics. His experiments with prisms helped show that white light contains many colors. In this lesson, however, our focus is not on memorizing Newton's biography. The important point is that Newton created a systematic framework for connecting forces with changes in motion. We will begin by clarifying what physicists mean by a force. To use Newton's laws correctly, we first need to identify the different ways in which objects exert forces on one another. A force is an interaction that can change an object's velocity or deform the object. Forces are often divided into two broad classes: contact forces and field forces. A contact force requires physical contact between objects. For example, when a hand pushes a box, the hand and the box are touching. When a table supports a book, the table exerts a normal force on the book. Friction is also a contact force because it acts where two surfaces touch. Other contact forces include tension in a rope, the elastic force from a stretched spring, and the resistance of air acting on a moving object, and things like that. A field force does not require direct physical contact between the interacting objects. Gravity is the most familiar example. Earth pulls an object toward even when nothing is visibly connecting the object to Earth. Electric and magnetic forces can also act across empty space. A charged object can attract or repel another charged object, and a magnet can affect another magnet without touching it. The words contact and field describe how the interaction appears at the scale of the problem. In introductory mechanics, this classification helps us identify which objects are interacting and which forces should appear on a force diagram. When analyzing an object, always ask two questions. What other objects is exerting each force? And in what direction does that force act? Although many everyday forces appear different, modern physics describes all interactions in terms of a small number of fundamental forces. At the most fundamental level, physicists describe nature using four basic interactions. The first is the gravitational interaction. Gravity acts between objects that have mass. It is the weakest of the four fundamental interactions, but it dominates the motion of planets, stars, and galaxies because it acts over very large distances and is always attractive. The second is the electromagnetic interaction. It acts between electrically charged particles. The third is the strong nuclear interaction. It acts at very short distances and helps bind quarks together inside protons and neutrons. The residual strong interaction also helps hold the nucleus of an atom together. The fourth is the weak nuclear interaction. It is involved in certain radioactive decay processes, including beta decay and in reactions that occur inside stars. At the level of modern physics, these interactions are described using fields. In an introductory mechanics course, however, we will mainly work with familiar forces such as gravity, normal force, friction, tension, and applied forces. The key idea is that the many forces encountered in everyday life can ultimately be traced back to a small number of fundamental interactions. No matter which interaction produces a force, force has both magnitude and direction. That means force must be treated as a vector. Force is a vector quantity. Therefore, a complete description of a force requires both magnitude and direction. We represent a force with an arrow. The direction of the arrow shows the direction of the force, and the arrow's length represents the magnitude of the force when a consistent scale is used. On this slide, the 15 Newton force is represented by a longer arrow than the 5 Newton force because 15 newtons is 3 times as large as 5 newtons. However, we cannot compare forces by magnitude alone. Direction matters. If a 15 Newton force points to the left and a 5 Newton force points up and to the right, we cannot simply add or subtract 5 and 15. The forces do not act along the same line. We must add them using vector addition, often by resolving the force into x and y components. This is why force diagram is so useful. It allows us to see which forces reinforce one another and which forces oppose one another and which forces act in perpendicular directions. The vector sum of all forces acting on an object is called the net force. The net force determines whether the object's velocity changes or not. Before calculating net force, we also need to distinguish force from another important physical quantity, mass. Mass is an inherent property of an object and is a measure of how strongly the object resists a change in its velocity. Mass does not depend on the object's location. An object has the same mass on Earth, on the Moon, or in deep space. Mass is also independent of the method used to measure it. Different reliable measurement methods should give the same value. Mass is a scalar quantity. It has magnitude but no direction. So masses combine using ordinary arithmetic rather than vector addition. The SI unit of mass is the kilogram, abbreviated as kg. It is important to not confuse mass with weight. Mass is an intrinsic property measured in kilograms. Weight is a gravitational force measured in newtons. A person's mass remains approximately the same on Earth and on the Moon, but the person's weight is smaller on the Moon because the Moon's gravitational field is weaker. Later, Newton's second law will show us quantitatively how mass affects acceleration. For now, remember that greater mass means greater resistance to change in motion. With force and mass defined, we can now state Newton's first law and examine what it says about motion when the net force is zero. Newton's first law states an object remains at rest or continues moving at constant velocity in a straight line unless it is acted on by non-zero net external force. This law describes two situations. First, if an object is at rest and the net force remains zero, the object stays at rest. Second, if an object is already moving and the net force remains zero, it continues moving with constant speed in a straight line. The phrase constant velocity is important. Velocity includes both speed and direction. Therefore, an object traveling around a curve is changing velocity even if its speed stays constant. A net force is required to produce that change in direction. Newton's first law does not say that no forces are acting, it says that the vector sum of all forces may be zero. For example, a book resting on a table experiences a downward gravitational force and an upward normal force from the table. These forces balance, so the net force is zero and the book remains at rest. A hockey puck gliding across nearly frictionless ice can continue moving at almost constant velocity because very little net horizontal force acts on it. In everyday life, friction often slows moving objects. That can make it seem as though force is needed to maintain motion. But Newton's first law shows that force is needed to change motion, not to maintain constant velocity. To apply Newton's first law, we must be able to calculate the net force from all individual forces acting on an object. The net force on an object is the vector sum of all external forces acting on the object. The SI unit of force is the Newton, abbreviated as capital N. In this example, a 10 Newton force acts to the right and a 4 Newton force acts to the left on a box. Because the forces act along the same line but in opposite directions, we can choose right as positive and left as negative. The net force is therefore positive 10 newtons minus 4 newtons, and that is equals to positive 6 newtons. So the net force is 6 newtons to the right. Notice that the net force points in the direction of the larger force. A 6 Newton net force does not mean that only one force is acting. It means that the combined effect of the two forces is equivalent to a single 6 Newton force directed to the right. Because the net force is not zero, the object's velocity must change. The direction of its acceleration will be to the right. The object could speed up while moving right, slow down while moving left, or change direction depending on its initial velocity. The force direction alone does not tell us the object's current direction of motion. It tells us the direction in which the velocity is changing. When forces are not along the same line, ordinary subtraction is no longer sufficient. We must add their perpendicular components. Now consider two perpendicular forces acting on the same object. A 4 Newton force acts to the right and a 3 Newton force acts upward. Because these forces are perpendicular, the net force is the diagonal vector obtained by adding them head to tail or by using components. The horizontal component of the net force is 4 newtons and the vertical component is 3 newtons. We calculate the magnitude using the Pythagorean theorem. So the magnitude of the net force is equals to square root of 4 newton squared plus 3 newton squared. And we get square root of 25 newtons squared, which is 5 newtons. To find the direction, let theta be the angle between the horizontal direction and the vector. So we can use the equation theta equals tan inverse and then the y component 3 Newton divided by the x component 4 Newton. And this is equals to 36.9 degrees, which is approximately 37 degrees. Newton's first law is closely connected to inertia. Inertia is the natural tendency of an object to resist a change in its state of motion. An object at rest tends to remain at rest, and an object moving with constant velocity tends to continue moving with that velocity unless a net external force acts. Mass is a quantitative measure of inertia. An object with greater mass has greater inertia and is more difficult to accelerate, decelerate, or redirect. For example, it is easier to change the motion of an empty shopping cart than a fully loaded cart. The loaded cart has greater mass and therefore greater inertia. Inertia is not a force, it is a property of matter. We should not draw an inertia force on an ordinary free body diagram. Newton's first law is valid in inertial reference frames. An inertial reference frame is one that is not accelerating. That means the reference frame is at rest or moving at a constant velocity. A reference frame accelerating relative to an inertial frame is non-inertial. For example, inside a car that suddenly accelerates forward, a passenger may feel as if a force pushed them backward. In an inertial frame outside the car, the passenger's body is simply resisting the change in motion while the car moves forward beneath them. This gives us the central message of the lesson. Forces are vectors. Their vector sum is the net force. If the net external force is zero, an object remains at rest or moves with constant velocity. Mass measures how strongly the object resists changes in that motion. Before ending, consider this question. A spacecraft is moving through deep space with its engines turned off and no significant external forces acting on it. What happens to its motion? It continues moving in a straight line at constant speed. It does not naturally slow down simply because the engines are off. That is Newton's first law.